Hello everyone. This video is on solving linear first-order differential equations that are in what's considered standard form, or we're going to take a linear first-order differential equation and put it into standard form, and then solve using what's called an integrating factor. And you'll see when we get. I have 3 examples in this video, so let's just get into it. So I have the following instructions for all 3 examples. I'm asked to find the general solution of the given differential equation. And again, these are going to be first order linear differential equations. Then we'll give the largest interval I over which the general solution is defined. And then finally, determine whether there are any transient terms in the general solution. And I'll talk about what it means to be a transient term. Alright, so in my first example here, I've got dy dx, the derivative of y with respect to x. So here we're treating y as the dependent variable, x as the independent variable, equals 5 times y. Now, I know that you're probably thinking, hey, this is, if you remember previous videos I've put up or whatever reading you've done, you think, hey, this is a separable equation. Right, so I could solve this the way you solved any separable equation. In fact, I'll do that real quickly off to the side. Right, so I'm noticing, hey, this is separable. And we can get the y's on one side, right, dy over y. And then the x is on the other, equals 5 dx. Integrate, we have the natural log of the absolute value of y equals 5x, plus some constant. Then now this is an implicit solution, family of solutions. I want to solve for y though. If I want to get an explicit solution, exponentiate both sides. E raised to this would be equal to e raised to this, and I'll call this c1 actually because I'm going to be changing it. So it's constant 1. So over here now I have just y equals. And here e to the 5x plus c1, that would be e to the c1 times e to the 5x, and e to a numerical power, e to a constant, is another constant. So I'll call this c2 or something, or just c in general because c is different than c1. So c, some constant, right? This is a constant, times e to the 5x. And here we go. This is an explicit solution, a general family of solutions here, one parameter family to this differential equation. And the largest interval over which it's defined would be all real numbers. It's e to the, and it's an exponential. It's defined everywhere. And transient terms Alright, transient terms, these are the terms that approach zero, as the value of the independent variable gets larger, goes to infinity. Right, as the value of the independent variable, which in this case I'm treating x as the independent variable. Well, as x goes to infinity, e to the 5x would also blow up, right? Would also go to infinity. So this has no transient terms. Okay, so there, I did the problem, when I thought about it as a separable equation. But not every equation is separable. Right? Not every linear first-order differential equation is separable. So something else you're going to be able to do is write a first-order linear differential equation in standard form. All right, so here's the standard form of a first order linear differential equation. Okay, looks like this. So you have a dy over dx, or dx over dy, or dr over d theta, dt over ds. Just pay attention to what's being treated as the dependent variable and what's being treated as the independent variable. So I have the first derivative of the dependent variable with respect to the independent variable, in this case y and x, plus then some function of the independent variable p of x multiplied by the dependent variable y. Alright, so the zeroth derivative of the dependent variable, and then equal to some other function of the independent variable x on the other side. Okay, so this is called the standard form for a first order linear differential equation, and this would be in y, right? You have y to the first, and then the zeroth derivative of y here, the first derivative of y. So this is a differential equation in y. Just again, sometimes the variables will be different. You could even sometimes interchange the role of x and y, as we'll see in an example I have later. I'm going to go over 3 examples. All right, so what I'm going to do is put this equation into this form. All right. And this one's pretty simple. So just keep the dy dx on its own side, and I would just simply need to subtract 5y, and then you have 0 on the other, and there, this is in standard form for a linear first order differential equation. Right. Now, how do we approach solving an equation that's in this form? We're going to be using something called an integrating factor. All right, multiplying both sides by an integrating factor. Now you can read your textbook as to how this is developed. It really comes from like the product rule. You'll see when I get to the multiplication here in a second. So I'm just going to write what the integrating factor is. I'm not going to develop it. I'll call this I. And the integrating factor is going to be e raised to the integral of p of x dx, right, where p of x is just this coefficient of y when it's in standard form. All right. And what you do with this is you multiply both sides by this integrating factor, and you'll see how it helps in a second. Right? And again, I'm going to do 3 examples of this, so hopefully you see what's going on after 3 of them. Multiplication on both sides, right, by this. All right, so for this particular example, the integrating factor for this one here would be e to the integral. Now the p of x, notice it's plus p of x times y. The p of x would be this -5, right? That's the p of x in standard form here. So I'd have e to the integral of -5 with respect to the the independent variable x. Right. So this is e, and then the integral of -5 with respect to x would be -5x. And don't worry about plus constant. We'll just use the basic antiderivative here. All right, so now what I'm going to do, multiply both sides of the equation in standard form here by e to the -5x. So I've got e to the -5x times dy dx minus 5 times e to the -5x times y equals, and then 0 times anything is 0. Now the whole reason for multiplying by this fancy integrating factor here, I'll put in a box for you. the whole reason we're multiplying by this is to get an expression that would result from the derivative of a product. Hopefully you can see that this is just the derivative of this product of e to the negative 5x times y with respect to x, isn't it? Right. And check it out, right? Now if you were to do the product rule, you have the first factor, e to the negative 5x times the derivative of the second, dy dx. And then plus, and then the derivative of the first factor, negative 5 e to the negative 5x times y, times the second, times y. And then over here you have just 0. And then now this is separable. Right? Now this is separable. Right? So I can separate the differentials. Right? Not really separate the variables, but just separate the differentials. So I have d e to the negative 5x times y equals 0 dx, putting the dx over here. And integrating both sides. Remember, this integral symbol kind of just undoes a differential. And the integral of a differential is just the function itself, right? So what's left over here is e to the negative 5x times y. And then the integral of 0 with respect to x, the antiderivative of 0 is just a constant. So I'll say c, right, where c is a constant. And then we can solve for y. Well, in order to do that, I would just multiply by e to the 5x, and we get y equals some constant c times e to the positive 5x. And there you go. There's the general solution written explicitly, right? Solve for y of this differential equation. All right, so that's with this integration factor. And this integrating factor is going to come into play for each of these examples. So if you didn't get it now, hopefully you get it after I'm done with 3 of these. Well, look at this. I mean, when I treated it as when I said, oh, this is separable and did it that way, I got the same thing. Y equals some constant times e to the 5x as the general solution. And, again, the largest interval over which this is defined is, all real numbers. Right? This is an exponential, and it's defined everywhere. And as I mentioned before, no transient terms. Again, a transient term is any term that would approach 0 as the value of the independent variable goes to infinity. Well, as x goes to infinity, this term would just get larger and larger, right? Not go to 0. Or go to negative infinity if this is a negative constant, but no transient terms. Right. Okay, wonderful. So yeah, so when we're focusing on this, right, this whole video, putting things in standard form and then multiplying both sides by this integrating factor, and then going from there. All right. Also, too, like I've done in previous videos, if you've seen them, since this is a first order linear equation, I'd like to look at the slope field just for fun. So here I have a slope field generator from Desmos. Right? If you look up, just do a search for slope field generator. The one made in Desmos comes up first, and here we had this g here is the y prime. Dy dx was equal to 5y. Right? That was the equation. All right, so there we go. Slope field where dy dx is equal to 5y. And then I'm just going to graph, y equals some constant times e to the 5x. Y equals, now, I'll just have the constant be 1, this e to the 5x, and you can see this red graph popping up here. See how it follows the slope field pretty well? And again, you can replace c with anything. Y equals 2 times e to the 5x. So it's still following the slope field pretty well, right? Going flowing in the same direction. Now if c were negative, you just have it flowing downward, right? Negative 2, and it flips it over, and you see how it's again following the slope field. Right, so any constant times e to the 5x is a solution curve to this differential equation. Right. Okay, but so that first example was a little easy because it was separable. You didn't have to do it this way with the integrating factor. And if you notice that, if you like separable equations, maybe those will be easier for you. But not every equation is separable. All right, like the next example. All right, next example, I got the same instructions. So find the general solution of the given differential equation. Give the largest interval, call it I, over which that general solution is defined, and determine if there are any transient terms in that general solution. All right, so there's another one with y's and x's. Again, they don't have to be y's and x's. And yet again, it looks like we're treating y as the dependent variable, and we're treating x as the independent variable. Okay. So again, let me pull up what that standard form was. It's right here. So here was the standard form. Let me get that differential equation out of the way. Right. So I'm going to try to write this equation here in standard form, because notice this is not separable. All right. Try as you might. I mean, you may be able to make some sort of substitution to turn it into a separable equation, but nothing comes to mind. All right. Yeah, you can do all you want. I don't see how you could turn this, you could get all x's on one side and all y's on the other. I just don't see how that could happen. All right, so here we have a non-separable equation in x and y. And in order to get in this particular form, you need the coefficient on the y prime is 1. So here it's x. Right? So I'm going to divide through by x. So we have dy dx, then minus 1 over x times y, because again I'm dividing everything by x, equals, and then dividing this side by x, you get one of the x's cancel, and you get x times the sine of x. Right. Great. So now it is in this form. Right? I got the derivative of my dependent variable with respect to my independent variable, plus some function of the independent variable, which is this negative 1 over x. That's the p of x that's mentioned in the form, times y, times the dependent variable, equals, and then over on the other side, another function of the independent variable. So that's the f of x. All right. So now that I've got it in standard form, I'm going to find that integrating factor, which again I'll call I here. Now I know I said I was going to be the interval, but we'll do, this is integrating factor. All right, just don't confuse them. I guess you could call it I of x if you wanted, just to avoid confusion with the other I that's going to be an interval. And this is e, and it's I of the independent variable, e raised to the integral of p of x dx. So in this particular example, it's e raised to the integral of negative 1 over x dx, which is e to the negative, natural log of the absolute value of x, and then don't worry about the plus constant, right? For this integrating factor, we're just going to use the basic antiderivative. And putting the negative 1 as in here, you'd have e to the natural log of the absolute value of x to the negative first, which is just x to the negative first. 1 over x, basically. 1 over x is the integrating factor. All right, so now what I'm going to do is multiply the standard form here by 1 over x every single term. So now I have 1 over x times dy dx minus 1 over x squared. Right? 1 over x times 1 over x would be 1 over x squared times y equals, and then multiply this side by 1 over x, and the x is canceled, you just got sine of x. And again, the whole reason for finding this e to the integral of p, right, this integrating factor, and multiplying both sides by it, is so now this left side is actually the derivative of some product. Right? This is the derivative of the following product. It's the derivative of the integrating factor times y. Right, just like in the previous, with respect to x. Sorry about the bottom of the page here, over dx. And you can check that out, take the first times the derivative of the second, plus the second times the derivative of the first, right? You're getting all that here. Equals sine of x, and then I can take the dx to the other side, and then we'll integrate and solve for y. Right? So I have the differential of 1 over x times y equals the sine of x dx, and we're going to do the antiderivative of both sides. And this is, again, the antiderivative of a differential. They undo each other, and I'm just left with 1 over x times y. And then over here, right, the antiderivative of sine of x was negative cosine of x. And then I'll put the plus a constant, right, plus some constant over here. All right. And then to solve for y, I simply multiply through by x. So y equals negative x times the cosine of x plus c times x. All right. Great. Where c, again, c is any constant. So there we go. Here's a great general solution. Right, general solution to this differential equation. Now comes the tricky part, I guess. The interval, the largest interval over which is defined. Well, remember how up here I divided through by x, so at some point you have 1 over x. Right? You got 1 over x here, you got 1 over x there. So x cannot be 0. Right? So I can't just say, oh, this is a polynomial, this is a cosine function. Those are defined everywhere. The largest interval over which this is defined can't include 0. Right? Because I divided by x at some point, and you can't divide by 0. So it's the entire real number line without 0. So, and again, you can't have any breaks in it. Right? So either it's going to be to the right, all the numbers to the right above 0, all the numbers below 0. So I'll say this one. The largest interval over which is defined is this interval here, from 0 to infinity, but not including 0. Or you could have also said that it's from negative infinity to 0. They're the same. These are kind of like the same size, but I'll stick to the ones with positive values in it. All right, and then finally, are there any transient terms? Again, no. As x approaches infinity, this term would approach negative infinity. Because this cosine of x is always between negative 1 and 1, but this would blow up. Actually, this would kind of fluctuate back and forth between negative infinity and positive, but it's not going to 0. Is all I'm saying. As x goes to infinity, this term would not go to 0, and this term would not go to 0 for any non-zero constant. Right. So again, we have no transient terms. And be careful. I mean, I know so far, and I think even my third example has no transient terms, so I apologize about that, but just because the examples in my video have no transient terms doesn't mean you're never going to see that. Right, if you're reading your text, looking at examples, you should see examples or come across problems where there are transient terms. You know, there are terms that approach zero as the value of the independent variable gets larger and larger. Okay, so again, since this is a first order differential equation with you know, the y as the dependent variable, x as the independent variable, since I have it like that, I want to look at the slope field. All right, so what I'm going to do is I'm going to solve for dy dx here. So let's make it y over x plus x sine x. All right, let's look at this. So y prime here, dy dx will be y over x plus, and then x times the sine of x, and just make sure you got things in radian mode. All right, so there's the slope field for this differential equation. And then let's put in one of our solutions. You know, we had y equals negative x times the cosine of x plus some constant times x. So how about just 1 times x? Yeah. And look at this. You know, some constant times x. Look at this graph. See how it's following the directions of the slope field? It looks like, you know, see it goes up here, then it's got to go down, and then look, all these slopes are going up, and then see how the curve is going up, and then the curve is going up, and no, the slopes are going down, the curve is going down, the slope is going up, and the curve is going up. And again, you can replace this constant in front of x with anything. Here's, you know, plus 3x. Again, following along the slope field. It could be minus even, right? A negative constant, you know, minus 5x. And there, it's pretty straight up, but you know, little curve. There you go. So you're following the slopes pretty well. Okay. So it seems reasonable to me that this is indeed a good. These are general solutions. For this differential equation. So far so good, hopefully. Hopefully you're getting this a little bit. You know, the standard form of a first order linear differential equation. This integrating factor, right? This integral of e to the px dx. And multiplying both sides by the integrating factor, and then integrating and solving. All right, now I've got one last example. And so far, right, in my first two examples, and in most examples we've seen in my videos, in other, you know, for separable equations and whatnot, so far we've treated y as the dependent variable and x as the independent variable. That doesn't always have to be the case, right? Like I said, the role of x and y could switch. All right, so here's a differential equation, first order. I have y times dx, the differential of x, minus 4 times the quantity x plus y to the 6th dy equals 0. Now look what happens. Look what happens if we treat like we normally do. If we treat y as the dependent variable and we treat x as the independent variable. Right, so that means we want, you know, to see dy dx in the equation. Look what happens when we do this. You know, I would want dy dx, so I divide everything by dx, and again, you can only do that kind of manipulation with first order differentials. I divide everything by dx, so we get y minus 4 times x plus y to the 6th dy dx, you know, equals and then 0. And look at this. Now I have my first derivative there, but you see how the coefficient of the first derivative doesn't depend on just the independent variable. It also depends on y. So this equation, if you think back to how to classify linear equation, classify differential equations, because of this y to the sixth in this coefficient here of the first derivative of y, this is non-linear. This is a non-linear differential equation. Oh no. All right. I'm supposed to be looking at how to solve linear first-order differential equations. So if we treat y as the dependent variable and x as the independent variable here like we normally do, something bad happens. Right? I get a non-linear equation, and I don't like that. So instead, this is bad. Right, that doesn't mean we can't solve it. There might be some other things we see in the future on how to solve nonlinear equations, but instead, let's switch the role of x and y. Let's treat x as the dependent variable and treat y as the independent variable. So when I find my solution, it's going to be x equals, right? X is going to be a function of y this time. All right, so let's treat x as the dependent, y as the independent. So that means we're looking for dx dy, right? I want in my equation, I want derivatives of x with respect to y. All right, so let's see what happens when I do that. Now, in order to get that, I need to divide through by dy. So we would have y times dx dy. Then what I'm going to do here is distribute this -4. So we'd have minus 4x, and then minus 4y to the sixth, and I divided by the dy equals 0. And now hopefully you see that this is a linear equation in x. This is a linear differential equation, right? Because if I treat x as a dependent variable, see I got x prime, I got dx dy, got x here, and look at the coefficients on the x prime and x. The coefficient depends on just at most, the independent variable. See this, the coefficient of dx dy depends on just y and not x. The coefficient of x is -4, which depends on at most y and not x. And then you've got some other term depending on the independent variable y. So this is by classification a linear differential equation in x. And this is what I want. This is good. All right, so we're gonna look at it this way and treat x as the dependent variable, y as the independent variable. So now what I would like to do is get it in standard form. All right, I'd like to get it in standard form where I have we can get dx dy. Hopefully you can see how this would be done with some algebra here. Then I'm going to divide everything by y, right, to get the coefficient on the derivative to be 1. So I have minus 4 over y times x, and then equals, and I would add 4y to the 6th, then divide by y, so I'd have 4y to the 5th on the other side. Right. And this, right, this is in that standard form. Just switch the role of x and y. Right. Again, we're treating x as the dependent and y as the independent. So you see if I switch the x and y, and change x to y here, I've got dx dy plus some function of y times x equals some function of y, which is exactly what I have down here. Right. So yeah, just pay attention, be careful, pay attention to what variable is playing what role, right? What variable is playing the part of the independent variable and what's playing the part of the dependent variable. All right, so here's this linear equation in standard form now. And again, I'm treating all the independent variable as y, so this is p of y, and over here is f of y, back in that little form. So when I find the integrating factor, it's this, right? So the integrating factor is now a function of y. So I'll say I of y equals e to the integral of p of y dy, right? Because again, now the independent variable is y. I'm saying that a bunch. So that'd be e to the integral, and p of y is this negative 4 over y. So this would be e to the negative 4 times the natural log of the absolute value of y, which ends up just being y to the negative 4th, right? Or 1 over y to the 4th, if you want to think of it that way. All right, now multiply everything on both sides by this integrating factor, right? 1 over y to the 4th. In doing that, I'd have 1 over y to the 4th times, the derivative of x with respect to y minus 4 over y to the 5th times x equals 4y. Right, multiplying everything by y, 1 over y to the 4th. And again, the whole point of doing this is so I get this left side here to be the derivative of some product, right, where the product rule was used. This is actually the derivative of 1 over y to the 4th, or y to the negative 4th, times x with respect to y. Right, with respect to the independent variable is now y. Got to be careful. And then over here, and you can again do the product rule. First times the derivative of the second with respect to y, plus the second times the derivative of the first with respect to y. Right, equals 4y. And then I'll separate the differentials. 4y dy. And do the integral on both sides. Again, the integral of a differential, they undo each other. I'm left with this product here. So 1 over y to the 4th times x equals, and then over here, this would just be a 2y squared. All right, 2y squared plus some constant. Right, and then I would multiply through, and then now this time we're solving for x. Remember, I'm treating x as the dependent variable, so we're getting x as a function of y. So I solve for x, multiply by y to the 4th, and finally we have x equals 2y to the 6th. Right, 2y to the 6th plus some constant times y to the 4th. Where again, c is a constant, and there's your general solution to this differential equation. All right. Now, same deal. Right, talking about intervals over which this is defined, you're going to be thinking about like y coordinates. Right? Notice here I have a 1 over y to the 4th that I multiplied everything by. Earlier I divided by y, right, when I was trying to write it in standard form here. I divided everything by y. So y can't be 0, right? Y can't be 0. So if you're talking intervals on the y-axis for which that's defined, we're talking about y going from 0 to infinity, right? Would be the largest interval over which that's defined. Or you could go from negative infinity to 0. But again, this is on y-axis, right? Because again, y is being treated as the independent variable this time. And once again, no transient terms. As the independent variable goes to infinity, as y goes to infinity, this term would not go to 0, this term would not go to 0. So again, I have no transient terms. This isn't always going to happen. I just happened to pick 3 examples where there are no transient terms, and I apologize about that, but you will eventually see examples where some of the terms that depend on the independent variable would approach 0, as the value of the independent variable goes to infinity. All right, wonderful. Okay, and then if you wanted to use slope fields for this, you could just switch the role of x and y. All right, just actually switch the letters. So like if I just switch every x with y here and solve for dy dx, right? If I just switch the y's and x's, you know, and we'd have dy dx, and this would be y over x. So I would add that, so 4y over x, and then, you know, plus 4x to the fifth, right? I'll just write it this way if I'm looking for a slope field, right? So if I graph that, I'll put up the slope field here. So 4y over x plus 4x to the fifth, right? And then for my solution, right, the solution here, right, that's a pretty crazy slope field there. Not a lot defined, it looks like. Then for my solution, you know, I'll graph y equals 2x to the 6th plus some, you know, multiple of, well, x to the 4th. Right? Just switching x's with y's and y's with x's. Oops, wrong switch. So y equals, you know, 2x to the 6th. And then that should be enough, really. Yeah, you see how it's kind of following the slope, and then plus any multiple of y to the 4th. You know, I could add y to the 4th, sorry, x to the 4th. You see how that, I mean, there's not a lot of slopes drawn here in this program, but you see how, you know, it follows pretty much the directions that these slopes are going in. So it kind of leads me to believe that this is pretty good. Right? This is a good family of solutions. Now I guess another way you could also enter the slope field would be, instead of switching the x's and y's, you could leave it this way and then just solve for dx dy. Right? Dx dy would be, you know, 4x over y plus 4y to the 5th, which if you put this as a single fraction would be 4x plus 4y to the 6th divided by y, and then you flip that, right, to get dy dx. And you can, again, you can only do this with first order differentials. So let me flip that and put, you know, y over 4x plus 4y to the 6th. See what I get there. So y over 4x plus 4y to the 6th for the slope field. Alright, this might be actually too crappy. Because then if I graph x equals 2y to the 6th, maybe not, plus y to the 4th. Yeah, so I guess it's looking pretty good. I mean, the curve is following, like, I mean, there's not a lot of slopes drawn, but the curve that I just drew here, x equals 2y to the 6th plus some constant multiple of y to the 4th, looks like the curve is, you know, following these slopes in the same direction pretty well. So again, be careful. The whole point of this last example is just to remind you that, you know, and play around with it. You know, if you have two variables in an equation, try looking at it in one way where you treat, you know, maybe one variable is dependent, the other variable is independent. And if for some reason the equation ends up nonlinear that way, then you know, maybe not the best choice. Try looking at it the other way, right, where the other variable is the dependent variable and the first one was independent, and see if you can come up with a linear equation, because we want to focus on linear equations here. All right. So again, sorry about that. You know, no transient terms showed up, and this was a bit long. So again, apologize. Hopefully it's not too long, but I mean, it's almost 45 minutes, pretty long. Hopefully watching me go through these three helps you when you're working on problems similar to this, when you recognize it's a linear first order equation, put it in standard form, get that integrating factor, multiply on both sides by the integrating factor, separate the differentials, integrate, and solve. I know it's a lot to do, but it's doable. And thank you very much for watching.